What would we see if we approached the speed of light? Our journey will take us aboard a hypothetical spacecraft accelerating away from Earth, moving faster and faster. As we gain speed, we encounter a series of intriguing optical and physical effects that challenge our understanding of the universe. Let's embark on this journey of discovery and explore the key points and relevant details on the topic. Our spacecraft begins its journey from a state of relative rest with respect to Earth. Once launched, we start to accelerate gradually, propelled by a hypothetical propulsion system that allows us to constantly accelerate for as long as we want. As we gain speed, we move away from Earth, accelerating ever further. An important point to highlight is that, contrary to what we might imagine, speed does not directly affect our bodies. When two trains cross, it is impossible for a passenger to feel whether it is their own train that is in motion. Similarly, inside the spacecraft, we cannot feel its speed, only its acceleration, which presses us against our seats. As long as this acceleration is reasonable, it will be perfectly bearable throughout our journey, even as we approach the speed of light. However, as we venture into deep space, there is a potentially deadly risk associated with very high speeds: a collision with interstellar dust particles. A simple dust particle could cause catastrophic damage to our spacecraft if it were to hit us at high speed. Fortunately, our ship is equipped with an advanced force field that acts as a protective barrier, repelling dangerous objects and ensuring our safety during the journey. Aberration of light and Terrell-Penrose rotation. As we continue to accelerate, we begin to notice the first optical effects of our journey. The stars ahead of us, which we are approaching, gradually appear to move away, and the sky in front of us seems to contract. This phenomenon is known as aberration of light and is caused by the fact that the light from the stars is still traveling toward us, taking some time to reach us. As we approach the speed of light, the intensity of light concentrates in front of us, while the sky behind us appears to expand and darken. Aberration of light also results in another intriguing phenomenon known as Terrell-Penrose rotation. Imagine that we are moving through a cosmic grid representing the structure of space. Normally, this grid would appear as a straight structure composed of converging straight lines due to perspective. However, as we accelerate, the aberration phenomenon distorts the image of the sky around us. Over time, the grid seems to contract in the direction of our movement, and the straight lines start to curve. This creates the illusion that objects in front of us are slightly tilted in our direction. This phenomenon is known as Terrell-Penrose rotation and is a direct consequence of relativity. Doppler effect and time slowing down. As our spacecraft moves farther away from Earth and approaches the speed of light, we begin to experience the Doppler effect dramatically. The Doppler effect is the phenomenon in which the perceived frequency of a wave, such as sound or light, changes as the source of the wave moves relative to the observer. In this case, as we move away from Earth, the light from the planet takes progressively longer to reach us. If we were to look through a telescope, we would see people on Earth moving in slow motion. Earth's clocks appear to run slower for us, and the light we receive appears to shift toward the red due to the stretching of the light wave. Ahead of us, the opposite happens. The spaceship approaches the light emitted by stars, making them appear brighter and shifting them toward the blue due to the shortening of the light wave. Special relativity and its consequences. As we continue to accelerate, our spacecraft approaches the speed of light, and we enter the realm of Albert Einstein's special relativity. One of the earliest notable effects of this theory is time dilation. According to relativity, an object's trajectory in space-time determines how time passes for it. As we accelerate and move away from Earth, our trajectory diverges from that of Earth, and our clocks measure a different time. This means that we would age less than people on Earth if we decided to return to Earth after our journey. This is one of the most intriguing consequences of special relativity and has been confirmed by scientific experiments. Another fundamental effect of special relativity is length contraction. When an object moves at a speed close to that of light, its length contracts in the direction of motion. This means that, as we approach the speed of light, objects in front of us would appear shortened in the direction of our motion. This phenomenon challenges our intuition but is a mathematically predicted and experimentally verified outcome. The limits of speed. As we approach the speed of light, all the aforementioned optical effects become extremely pronounced. As we reach the light rays ahead of us, they seem to come more and more from the front, while the rays of light behind us never manage to catch up with us. In our reference frame, the universe in front of us would be extremely contracted, appearing like a thin fabric that we would cross from side to side in fractions of a second. To an observer on Earth, we would be moving at the speed of light, but to us, the journey would seem instantaneous. We would move in the blink of an eye. However, physics imposes an insurmountable limit: the speed of light in a vacuum, which is approximately 299,792,458 meters per second. Nothing in the universe can surpass or even equal that speed, according to our current understanding of physics. As we approach it, our kinetic energy increases dramatically, and it would require an infinite supply of energy to accelerate further. Additionally, special relativity predicts that as we approach the speed of light, our effective mass also increases, making acceleration even more difficult. Therefore, it is strictly impossible for any object with mass to reach or exceed the speed of light in space. Faster than light travel, warp drive, and science fiction. However, human imagination and science fiction have led us to consider ways to bypass this seemingly insurmountable limitation. One of the most popular and intriguing ideas is that of the warp drive, popularized by the Star Trek TV series and movies. The idea behind the warp drive is that we wouldn't be accelerating a vehicle through space, but rather propelling the very fabric of space-time. According to Einstein's general theory of relativity, the structure of space-time can be dynamic and curve in various ways, primarily due to the presence of mass and energy. The idea of the warp drive is to create a bubble in space-time around our spacecraft and propel it faster than the speed of light. Our ship would remain stationary with respect to the surrounding space, while the space around us would move faster than light. This would open up the possibility of reaching distant destinations in a relatively short time, bypassing the limitation imposed by the speed of light. However, creating a warp drive is not a trivial task and is far from being achieved with our current understanding of physics. To create a warp drive bubble, massive amounts of energy would be required, along with the existence of an exotic form of matter known as exotic matter, which has reverse gravitational properties and so far only exists in the imagination of theoretical physicists. Furthermore, the warp drive theory faces significant conceptual and mathematical challenges, including the potential for violating causality, which raises questions about the consistency of the laws of physics in a faster-than-light travel scenario. The effects of a warp drive. Let's imagine for a moment that we were able to create a warp drive and accelerate our space-time bubble around the spacecraft. What would we see and experience inside that warp bubble? Looking from outside the warp drive, it would appear to emerge from nothingness, a region of intense space-time curvature. The space-time curvature would bend the path of light rays, creating a moving lens that splits into two parts, one advancing in the direction of movement and the other retreating in the opposite direction. Light travels slower than the warp drive itself. When light approaches the warp drive region, It hasn't had time to catch up with us yet, and after crossing the bubble, we begin to receive both the light that hasn't reached us yet and the light rays emitted after our passage. This effect would create a distorted and displaced view of the space around the warp drive. Inside the warp drive, our experience would be equally intriguing. Looking at the space in front of us, we would see the sky dramatically contract, becoming incredibly bright, while the universe behind us would appear extremely dark. A part of the sky would simply disappear from our view. The light emitted from that dark area is too slow to reach us, creating a region of permanent invisibility. Although current physics imposes limitations on the maximum speed we can achieve in space, the idea of the warp drive remains an exciting and inspiring dream that continues to challenge imagination and creativity. The quest for understanding these phenomena and overcoming their limitations remains an exciting area of scientific research as scientists explore the frontiers of knowledge and seek to unravel the mysteries of the universe.